Good morning, students. Hope you are all doing well. Welcome to the third lecture in the quadratic expressions. Hope you have watched the first two lectures. It would be easy for you to follow this lecture if you have watched those two video lectures. So, in this lecture, we are going to discuss some miscellaneous problems on quadratic expressions which are in exercise 3a, and we are going to discuss a theorem which is a necessary and a sufficient condition to have a common roots for two quadratic equations and related problems. Okay, now let us solve a problem. The problem looks like this. Here is the problem. If x1, x2 are the roots of ax square plus bx plus c is equal to 0 and c not equal to 0, and find the value of ax1 plus b whole to the power minus 2 plus ax2 plus b to the power minus 2 in terms of a comma b comma c. Now we have to write down, or we have to solve actually the solution of this. Here is the solution. Okay, given that x1 comma x2 are the roots of ax square plus bx plus c is equal to 0. This immediately implies we have seen the relations between roots and the coefficients of a quadratic equation. Let us write down that x1 plus x2 is equal to minus b by a, and x1 x2 is equal to c by a. Since x1 is a root of ax square plus bx plus c is equal to 0, implies by definition it has to satisfy that equation ax1 square plus bx1 plus c is equal to 0. If I take common x1 in the first two terms, what am I going to get is ax1 plus b plus c is equal to 0. This implies ax1 plus b is equal to minus c divided by x1. Here you can write x1 in the denominator. What is x1? x1 is actually a root. If at all x1 is equal to 0, that means one root of the quadratic equation is 0. If I substitute 0, then what do I get here? Ax square plus bx plus c, that is a into 0 plus b into 0 plus c is equal to 0. That means c must be 0. But it is given that c is not equal to 0. That's why x1 is equal to 0 is not a root actually. Okay. Similarly, ax2 plus b is equal to minus c by x2. Okay. Now we are going to find out this particular quantity. Let us find out that quantity. What is that quantity actually? 1 divided by ax1 plus b whole square plus 1 divided by ax2 plus b whole square, that is equal to 1 divided by minus c by x1 whole square plus 1 divided by minus c by x2 whole square. So that can be written as x1 square by c square plus x2 square by c square, that is equal to x1 square plus x2 square divided by c square. Now The numerator quantity can be rewritten as x1 plus x2 whole square minus 2 into x1 x2 divided by c square. So I substitute what is x1 x2, so it is minus b by a whole square minus 2 into c by a divided by c square. Now if I rewrite those things, what do I get is b square minus 2ac divided by a square into c square. So this is the final answer that I am going to get for this question. Right. Let us solve the next question. Here is the question. Find the condition that one root of the quadratic equation ax square plus bx plus c is equal to 0 shall be n times that of the other, where n belongs to z plus. Let us solve this problem actually. Solution. Here I have to find out the condition. Okay. Let alpha comma beta be the roots of the equation ax square plus bx plus c is equal to 0. Some relation is given actually. What is the relation? One root is n times that of the other. Okay, given that one root is n times that of the other. N times that of the other. Let me rewrite this one the other. Okay, let beta is equal to n alpha. Okay, we know certain relations between the roots and the coefficients. Let me write that alpha plus beta is equal to what? Minus b by a. This implies alpha plus n alpha is equal to minus b by a, implies alpha is equal to minus b by n plus 1 into a. Call it equation 1. Now we know the product of the roots is equal to c by a, implies alpha into n alpha is equal to c by a, implies alpha square is equal to c divided by a into n. We call it as equation 2. Okay, now substitute equation 1 in equation 2. We get minus d divided by n plus 1 into a whole square is equal to c divided by an. This implies b square divided by a square into n plus 1 whole square is equal to c by an. So we cancel a here and we rearrange the terms. N b square is equal to c into a into n plus 1 whole square. So the final answer is nb square is equal to ac into n plus 1 whole square. Here is the final answer. Right. Let us solve the next question. Here is our next question. If x square plus bx plus c is equal to 0 and x square plus cx plus b is equal to 0, where b not equal to c have a common root, then show that b plus c plus 1 is equal to 0. Let us let us solve this problem. Is not working actually. Let me check. Okay, now it is working. Here is the solution. Okay, let alpha be the common root of x square plus bx plus c is equal to 0 and x square plus sorry x square plus cx plus b is equal to 0. So since alpha is a root, this implies it has to satisfy the given equation. We get alpha square plus b alpha plus c is equal to 0. We call it equation 1. And similarly, I do it in the second equation also. So this is C alpha plus B is equal to 0. Call it equation 2. Now if I subtract equation 2 from equation 1, what do I get is alpha into B minus C plus C minus B is equal to 0, implies alpha into B minus C is equal to B minus C, implies alpha is equal to B minus C by B minus C, that is equal to 1. Of course, here B not equal to C, B minus C is not equal to 0, because we are writing B minus C in the denominator. We have to ensure that B minus C is not equal to 0. Okay. Now we have got alpha value is equal to 1. Since alpha is equal to 1 is a root of x square plus bx plus c is equal to 0, implies 1 square plus b into 1 plus c is equal to 0, implies 1 plus b plus c is equal to 0. Here we have proved, hence the solution. Okay, let us solve one more problem. The problem goes like this. Find a quadratic equation for which the sum of the roots is 7 and the sum of the squares of the roots is 25 actually. Now for this we need to find out the solution. Let us solve this question. here is the solution. So let alpha comma beta be the roots of the required quadratic equation. Here actually we need to find out the quadratic equation. So the equation whose roots are alpha comma beta is given by x square minus of alpha plus beta into x plus alpha beta is equal to 0. This result we have studied earlier. Now what is given actually? Given is sum of the roots is equal to 7 and sum of the squares of the roots alpha square plus beta square is equal to 25. So now we have alpha square plus beta square is equal to 25 implies alpha plus beta whole square minus 2 into alpha beta is equal to 25. Here our aim is to find out actually alpha plus beta and alpha beta in order to find out the equation. Already alpha plus beta is given to us, so we need to find out only alpha comma beta. So we focus on finding alpha into beta value. So this implies alpha plus beta is known, that is 7 minus 2 into alpha beta is equal to 25 implies 2 alpha beta is equal to 49 minus 25, that is equal to 24. So this implies alpha beta is equal to 12. Okay, we know the sum of the roots and we know the product of the roots. So the required equation is the required quadratic equation is x square minus 7x plus 12 is equal to 0. Yes. Okay. Next we will discuss a theorem. Okay. Here is a statement of the theorem. The statement goes like this. A necessary and a sufficient condition for the two quadratic equations a1x square plus b1x plus c1 is equal to 0 and a2x square plus b2x plus c2 is equal to 0 to have a common root is this condition c1 into a2 minus c2 into a1 whole square is equal to a1 b2 minus a2 b1 into A1 B1 C2 minus B2 C1. Okay, that means what actually they are telling is, suppose if at all equation 1 and equation 2 have a common root, then this condition, the coefficients need to satisfy this condition. The other way is, if at all any two quadratic equations satisfy the following condition, then the two quadratic equation must have a common root. This is what the statement tells actually. We are not getting into the proof of this. We'll try to solve some problems based on this particular theorem. Okay. Next, there is a problem actually. So here we are going to solve a problem based on the previous theorem. Now, the question is, if x square minus 6x plus 5 is equal to 0 and x square minus 3ax plus 35 is equal to 0 have a common root, then find the values of a actually. Let us find out the solution for this. Here is the solution. Let us write down. So for the given equations, let us write a1, a2, b1, b2, c1, c2. So here, what is a1 actually? A1 is 1 and b1 is equal to minus 6 and c1 is equal to 5. Okay. Now a2 is equal to 1 and b2 is equal to minus 3a and c2 is equal to 35 actually. Now the condition for common root is C1A2, apply condition for common root. Now let us substitute these values in that condition. So the first one is C1 into A2, that is C1 into A2, that is 1, minus C2 into A1, that is 5 into A1. A1 is C1 into A2 is 5 into 1 minus C2 is 35 actually, 35 into 1 whole square is equal to, so A1 into B2, A1 value is 1 into B2 value is minus 3 minus A2 value is 1 into B1 value is minus 6. So this is the one of the two terms. And the next one is B1 into C2. B1 is minus 6 into C2 is 35 minus B2. B2 value is minus 3a into C1 value is 5 actually. So we have substituted the values A1, A2, A3 in the above condition. Now, so this is 5 minus 35. Let us simplify this. So this is minus 3a plus 6 into minus 6 into 35 is minus 210 plus 5 into 3a is 15a. Now this value is going to be 300. Now if you observe it, we can take common 3 from both the terms. So this is going to be 3 into 2 minus a. This is going to be 5a minus 70. Now on both sides we can cancel 9. So this becomes 2 minus a into 5a minus 70. So this is 10a minus 140 minus 5a square plus 70a. So we rearrange the terms, we get 5a square minus 80a plus 240 is equal to 0. So in all these terms, you have 5 in common. So this implies if I divide it throughout by 5, I get a square minus 16 into a plus this is 48 is equal to 0. Now we have got a quadratic equation. Now we have to solve this quadratic equation. Now you can write a square minus 16a plus 48 is equal to, I can write this as a minus 12 into a minus 4. This implies the possible values of a are is equal to 0. This implies a is equal to either 12 or 4. So the possible values of a are 4 or 12 actually. So we have found out the value, or there are actually two values. One is 4, another one is 12. Okay. Now let's move on to the next question. Here is the next question. If a quadratic equations ax square plus 2bx plus c is equal to 0 and ax square plus 2cx plus b is equal to 0, where b not equal to c have a common root, then show that a plus 4b plus 4c is equal to 0 actually. It is very similar to that of a problem solved earlier. Anyway, I am going to solve this for you people. So yes, solution. Here is the solution. Okay. Let alpha be the common root of ax square plus 2bx plus c is equal to 0 and ax square plus 2cx plus b is equal to 0. So since alpha is a root, it has to satisfy both the equations, implies a alpha square plus 2b alpha plus c is equal to 0. You call it equation 1, and a alpha square means I am substituting alpha in the second equation. This becomes 2 into c alpha plus b is equal to 0. So this is equation 2. Now subtract equation 2 from equation 1. What do I get here is 2 into alpha b minus c plus c minus b is equal to 0 implies 2 alpha into b minus c is equal to b minus c implies 2 alpha is equal to b minus c by b minus c, that is equal to 1. Remember, b not equal to c implies b minus c not equal to 0. So what is that you have got here? So 2 alpha is equal to 1 implies alpha is equal to 1 by 2. So you have got the common root as 1 by 2. Now substitute alpha is equal to 1 by 2 in one of the above equations. In equation 1, we get a into 1 by 2 whole square plus 2b into 1 by 2 plus c is equal to 0. So that is a by 4 plus b plus c is equal to 0. So this implies a plus 4b plus 4c is equal to 0. Hence the solution. Now let us move on to the next question. Here is our next question. If the equations x square plus ax plus b is equal to 0 and x square plus cx plus d is equal to 0 have a common root and the first equation has equal roots, then prove that 2 into b plus d is equal to ac. So this is what we have to prove with the given conditions. Let us find out the solution for this. Here is the solution. So it is given that there is a common root for equations x square plus ax plus b is equal to 0 and x square plus cx plus d is equal to 0. Given that this you call it as equation 1 and this you call it as equation 2. Equation 1 has equal roots. So we know that the discriminant for delta 1 is equal to 0 for equation 1 in the by because roots are equal. So this implies b square minus 4ac is a square minus 4 into b is equal to 0. So we get this condition from equal roots and the roots of equation 1 are, what is that, minus b by 2a, that is minus a divided by 2 into 1, that is equal to minus a by 2. So alpha is equal to minus a by 2 is a double root for equation 1 actually. So this implies alpha is equal to minus a by 2 is one root of equation 2 because there is a common root in between 1 and 2. Okay. Now substitute alpha is equal to minus a by 2 in equation 2 actually. Why are we substituting? Because just now we have seen that alpha is equal to minus a by 2 is a root of equation 2. So this implies minus a by 2 whole square plus c into minus a by 2 plus d must be equal to 0 as it is a root. So this is a square by 4 minus ac by 2 plus d is equal to 0 implies a square minus 2ac plus 4d is equal to 0. Maybe we'll call this, we call this as equation 3 and we call this as equation 4. Substitute 3 in equation 4. What do we get is a square is replaced by 4b minus 2ac plus 4d is equal to 0 implies 4 into b plus c is equal to 2ac implies 2 into b plus c is equal to ac. So this is what is expected to prove. So we have got the solution, hence the solution. Thank you. Okay, let us solve one more problem on the condition for common roots. Here is the problem. Suppose that the quadratic equations ax square plus bx plus c is equal to 0 and bx square plus cx plus a is equal to 0 have a common root, then show that a cube plus b cube plus c cube is equal to 3abc. So this is what you have to prove. So let us find out the solution for this. Here is the solution. Now for the given two equations, we will write what is a1, b1, c1, a2, b2, c2. So you call this as equation 1, you call this as equation 2. For these two equations, we write what is a1, a1, b1, c1. a1 is a, b1 is b, and c1 is c. Now a2 is equal to b, b2 is equal to c, and C2 is equal to A. Now apply the condition for common root. So this implies, so if I apply that, it is C1, C1 is C into A2, A2 is B minus C2 is A into A1 is A. So this is my LHS. Now coming to RHS, A1 is A, into B2 is C minus A2 value is B into B1 value is B into B1 value is B into C2 value is A minus B2 value is C into C1 value is C. Now if I rewrite this, it is BC minus A square whole square, that is equal to AC minus B square into AB minus C square. Okay, now let us simplify the terms here. So this becomes B square C square plus A power 4 minus 2 into A square BC is equal to, it is A square into BC here minus A into C cube minus A into B cube plus B square into C square. Okay, now I think these two terms get cancelled, B square C square. Now let us rearrange the terms. So we get A power 4 plus A into C cube plus A into B cube is equal to 3A square BC. Now in all these LHS terms, I take common A, I get A cube plus B cube plus C cube. Here also I will take common A, it is 3ABC. Now I can cancel out A here. Why? A is not equal to 0. Why A not equal to 0? Because A is coefficient of equation 1. Because for an equation, this to be a quadratic equation, this must not be equal to 0. So we can cancel A here. So this implies A cube plus B cube plus C cube is equal to 3ABC, which is the required condition. Hence the proof of it. Okay, let us solve one more problem on condition for common roots. Okay, here is the problem. If x square plus 4ax plus 3 is equal to 0 and 2x square plus 3x minus 9 is equal to 0 have a common root, then find the values of a and that of common roots actually. Okay, let us find out the solution for this. Here is the solution. Here we write what is a1, a2, a3, so a1, b1, c1, a2, b2, c2. a1 here is 1, b1 here is 4a, and c1 here is 3. Now a2 here is 2 and b2 here is 3a and c2 is minus 9. Upon substituting in the given condition, what do we get is c1 into a2 is 2 minus c2 is minus 9 into a1 is 1. So this is my LHS term. whole square is equal to a1 is 1 into b2 is 3a minus a2 is 2 into b1 is 4a into b1 is 4a into c2 is minus 9 minus b2 is 3a into c1 is 3. So that is equal to 3a minus 8a, that is equal to minus 5a into minus 36a minus 9a. So this is minus 45a, that is equal to, it is 225a square. And 3 into 2 6, 6 into this is 15 square is equal to 225a square, implies a square is equal to 1, implies a is equal to plus or minus 1. Now there are two values, possible values for a. One is if a is equal to 1, what happens? Let us see. Let us find out the common roots in this case. So the first equation becomes x square plus 4 into x plus 3 is equal to 0, and this can be factorized as x plus 3 into x plus 1, implies the roots are minus 3 comma minus 1 here. Now the second equation becomes 2x square plus 3a, 3x actually, it is 3x actually, 3x minus 9. This can be written as 2x square plus 6x minus 3x minus 9 is equal to 0. I am factorizing it actually. So this is 2x into x plus 3 minus 3 into x plus 3 is equal to 0. So this can be written as 2x minus 3 into x plus 3. So this implies the roots are 3 by 2 comma minus 3. So the common root here is minus 3. Okay, now let me do the second case, the case 2. Case 2, if a is equal to minus 1, then the first equation becomes x square minus 4a plus 3. So in this case, sorry, actually I have to write x here, 4x plus 3. So this is x minus 3 into x minus 1 is equal to 0, implies x is equal to 1 comma 3. The roots are 1 comma 3 actually. Then the second equation is 2x square minus 3x minus 9. This can be written as 2x square minus 18 here minus 6x plus 3x minus 9 is equal to 0. Here this can be written as, if I take 2 common, it is x minus 3 plus 3 common, it is x minus 3 is equal to 0. So it can be factorized as 2x plus 3 into x minus 3. So this implies the roots for the second equation are x is equal to minus 3 by 2 comma 3. So the common root here is 3 actually. So if a is equal to if a is equal to if a is equal to 1, then the common root is minus 3. If a is equal to minus 1, the common root here is 3. Common root here is 3. Okay. The next concept is sine of a quadratic expression. Let us suppose that f of x is equal to x square plus ax square plus bx plus c. Let k be a real or a complex number. Let me denote f of x, f of k as ak square plus bk plus c. What is this f of k? That means I am given a real value. I am substituting that k in this expression. Whatever the value that I am going to get, that value I am denoting it with f of k. Then this f of k will have a positive sign or a negative sign, or is equal to 0. Let me understand through this example. Consider a quadratic expression f of x is equal to x square plus 2x plus 2. Okay. Now I am substituting a value, x value is equal to 1 in this expression. This is 1 square plus 2 into 1 plus 2, that is equal to 5, which has a positive sign. Now I am substituting x is equal to minus 1, which is minus 1 whole square plus 2 into minus 1 plus 2, that is equal to 1, which is positive. I'm trying with one more value, minus 2, x is equal to minus 2. I'm substituting in this expression. This is minus 2 whole square plus 2 into minus 2 plus 2. And this becomes 4 minus 4 plus 2, which is positive again. Looks like whatever real value I'm substituting, I'm getting positive only. Maybe we may think that, or you may think that, for some value of x, if I substitute, this might turn to be a negative number. Okay. Now, let me see. Now if you observe this f of x, this f of x can be written as x plus 1 whole square plus 1. This is our observation. That means this f of x can be written as x plus 1 whole square plus 1. Now, maybe this seems to be right. That means whatever, now if I give me whatever the real number you give me, if I substitute in this expression, this is going to be positive and plus 1. For a positive number, I am adding plus 1 here, then it is going to be a positive number. There is no chance, whatever the real number you give me, this cannot be negative. So, what's our observation here? The observation is, seems f of x is positive for all x belongs to R. Actually, we can say this f of x is positive for all x belongs to real numbers. Now, let me see some more examples. Let me discuss some more examples. Here are some more examples. Consider that f of x is equal to x square plus 2x plus 1. Here also I am doing the same business. I am substituting x is equal to 1 in this expression here. it is 4, which is positive. When I am substituting -1, here I am getting a 0 value. And when I substitute -2, x is equal to -2 in this, I am getting 2, which is a positive number. Now seems here also that expression, whatever the real number I am substituting, I am getting positive. Let me see whether our observation is correct or not. Now I can write my f of x as this x plus 1 whole square. Now you can tell if whatever the real number I am substituting in this expression, this is going to be positive. When x is equal to -1, this has become 0, that you have seen. That means whatever the real number I am substituting here, either I'll be getting 0 or a positive number. So this is our observation here. Seems f of x is greater than or equal to 0 for all x belongs to a real number. Actually, uh, we can say firmly that this expression is going to be greater than or equal to 0 for all x belongs to real number. Now, coming to this example, f of x is equal to x square minus 1. So first I am taking the value x is equal to 1. I am substituting here, it results me 0. I am substituting -1 here also, I get 0 here. And I am substituting x is equal to -2 in this expression, I am getting -2 square is 4. 4 minus 1, this is actually 3, which is positive. So f of 0 is 0 square minus 1, which is negative value. Now here the conclusion here is, if for some values of x it is taking 0, for some values of x it is taking positive, for some values of x it is taking negative. Let me rewrite this f of x. This f of x can be rewritten as this x minus 1 into x plus 1. Okay, what's our observation here? For some values of x, this expression is taking positive or 0. For some other values of x, it is taking negative. Now the question is, for what values of x this expression is taking a negative value, for what values of x this expression is taking a positive value. Now I got a question here. The question is, for what values of x, for what real values of x, a given quadratic expression takes a positive sign or a negative sign. How to find out for what values of x in real numbers a quadratic expression f of x is positive or negative? For this question, we'll try to answer this question in the next lecture with the help of some important theorems. Thank you.